Hi, and welcome to another Hopper on microcontrollers video. This video is going to cover some of the RP2350 boards. So based on the the Pi Pico 2, which has some clones already out that use this new chip from the Pi Foundation. So I'm using 3 different microcontrollers, and I've got real-time clocks here, and I've got some displays. So it's just going to be a general walkthrough of how Hopper works on microcontrollers and how you program different devices and with different drivers. So let's get started. So what is Hopper? Hopper is a modern semicolon and curly brace language, a little bit like Java or C Sharp, but it's designed to run on small devices. And by small, I mean very small, like 8-bit 6502s. So, 6502 board here. So Hopper runs on a 6502 board as well. So it can run on 8-bit microprocessors, but it also runs on microcontrollers, and it's designed to be easy to program in. And it's a structured programming language, so it's not like Python. It's more like C or C Sharp or Java. Unlike C on the Arduino, Hopper is a managed runtime, so it manages dynamic memory automatically. So there's no such thing as new and delete or malloc and free. It automatically. So this string here, it'll allocate and free the space for that string automatically. And when you assign new values to that string, it'll automatically garbage collect. So you're running around in this loop, continually modifying the string which contains the time. It'll automatically deal with that. So let's start with this one. This one's on the Adafruit board. So let's get rid of the other ones. Which one's the Adafruit one? This one? Yes. So let's get rid of this one. So this one's running on a battery right now. So standalone. So we put that aside. This one's also got a battery backup on the real-time clock. So if I turn the power off, it's off now, and then plug it in and restart it. It should keep the time, so it still knows what the time is. Very good. So let's put that one aside, and that one can be put aside. And we're looking at this one. So what have I done here, right? So again, this one also has a battery backup on the real-time clock. So in this case, I've used a doubler for Pi Pico featherboard, so you can put 2 boards on the. I'll show you what a doubler looks like. So if you're not familiar with the Adafruit's feather format, this is a doubler. So you can put 2 of their boards, 2 of their feather format boards on the same PCB, and these are the power rails at the back. There's 2 rails. Yeah, so you take one of those, you put a bunch of header pins on it, and then you put your microcontroller in one of them and your real-time clock in the other. And in my case here, I've broken out the I2C bus. So that's power over there, 3 volt, 3.3 and ground. And then these 2 here are clock and data for the I2C bus, which I've color-coded. My clock I always color-code to yellow, and my data for I2C I color code to green. So that's my I2C bus here. So power on those first 2 rails, and the clock and data on this rail. And then plugged into them, I've got 2 of these Adafruit 14-segment display LCDs, and they're on 2 different addresses. You can address them based on these jumpers here. So the ones on I think it's hex 71 and this is hex 70 as the 2 addresses. So, and I've got them sort of stuck together with a rubber band. And so let's go and have a look at what the code looks like to make all that work, right? And I'll take this apart once I've demonstrated the code, so I don't have to put it back together again. So let's go have a look. So the board is the Adafruit feather. So you first include which board you're using, and that's a board definition which tells it which pins are which peripherals and all that. So that's all a board definition looks like. And then when you include a board, it includes all the units used by that board. So And this unit is called board. And units are like units in Turbo Pascal. So they encapsulate the functionality of a module into one file. And then you can use namespaces, so board dot something to get to a board. And then there's a microcontroller unit. There's the I2C unit, which is, actually that's the wrong one, which is the wire unit, all that. It's got Arduino style APIs like digital write, analog read, all that. And you can jump around by double clicking on path names, or I can go control backspace to jump back to where I was. So I jump back twice. Okay, so Adafruit Feather, and then there's a folder in the Hopper environment. There's a folder called Boards, which has got all the board definitions. And there's a folder called Devices, which has got device drivers for all the devices I've already written device drivers for. So the 14-segment display from Adafruit is the one device. And that device will be a display device. And it uses a driver, which is the driver chip under displays, which is this HT16K33. And this is set up so that you can chain them together. So the number of modules in your display, so in my case, I've got 2 modules here. Each of them has 4 characters. For this example, there's only one module. Same display, just a blue one versus a yellow one. But here I've got one module, here I've got 2 modules, and you can chain as many of them as you like together by just adding modules. And when you add modules, it adds them to a list in the order you added them. So let's go have a look at that. So here on display, I'm adding modules. And the address, I2C addresses are, like I showed, the one was bridged with the least significant bit, so that'd be 7.1, and the other one's 7.0. And when you initialize, it initializes all of them. So that's how you set up your display modules. That's the display initialization for this device up here, this display. The other device we've got in this setup is this real-time clock here, and it's actually the data logger version, which has got a SD card slot on it. I've got another real-time clock from Adafruit here that doesn't have the data logger on it, but I'm using it for this one. So even though I'm not using the SD card, that's what this is here. I'm using the RTC SD Featherwing, so it's got SD card as well. To initialize that is a one-liner. Right. Now, we've all seen our fair share of flashing 12 clocks in the universe. And you could write some code to set the clock on this, and typically, like with Arduino, what they do is they take the time at the time of upload and they use that as the time, which is not quite as accurate as you want it. In my case, the Hopper debugger has the ability to set the time. So on your first run, if you're in the debugger, it'll get the time from the debugger client via the serial port, so via this wire. The one that's, the serial port is what we upload the programs with. It's what the debugger runs through. It's all just through the serial port. There's no extra hardware or extra wiring to make a debugger work with Hopper. So if you're running in the debugger, it'll actually get the time from the client, from the Windows machine that you're running on. And then what are we doing here? All these programs are very similar. That's why I'm describing this one in detail. So for this version, which is the Adafruit version, I've got 2 displays. So when I get the time, it's in this format. So it's 1, 2, 3, 4, 5, 6, 7, 8, conveniently 8 characters wide. And because on these 7 segment displays, that colon doesn't look that great. It's looks like 2 vertical bars. When I first put it up with colons, you couldn't really tell that this was the time, 10:55 a.m. 45 seconds, because I was enjoying showing the seconds. So I decided to flash it and, to blink the colon. And what I've got is I've got a counter. If for every second I'm running through this loop 10 times, so it's 100 milliseconds per loop. And if the counter is 0 or 1, then you'll see the colon. If not, it'll replace the colon with a space. So that's why it looks like the colon is lit for, 1/5 of the time there. Okay, so to build this, we hit F7. All the menu options up here that's build is F7. So they're up on the menu, but I can use shortcut keys as well. So it's pre-processing, compiling. You can see at the bottom of the screen here, optimizing. So it's building on my Windows machine. generating code, and it's done. Now if I press F5, the clock should stop. So we should stop seeing the blinking because it's going to load up. It's going to pause the Hopper monitor is going to break into this via the serial port, stop it, and upload a new program. So let's press F5 and see that happen. So there we go. It stopped blinking. It's frozen on the last time. We look at the bottom of the screen here. It says successfully uploaded our new iHex. So it's Intel hex file format of a Hopper executable. And then it's got a green bar at the top to show that we're in the debugger, not the editor anymore. And this black area on the right is the serial console that we're connected to with the debugger. So in the Hopper debugger, so we've uploaded it. We could run it now, but I'm going to run it. And I'm going to put a breakpoint on setting the time. So I've got a breakpoint there. That's what the pink line meant. I pressed F9 to get a breakpoint. So toggle breakpoint is F9. And now F5 will run to the breakpoint. So there we are. We've got as far as the breakpoint. It initialized the display, which cleared it. So we can now see it's blank again. And now if we set from debugger if we step into that F11 to step into that function, now we're in set from debugger. We step here. It's optimized code, so the breakpoints aren't exactly where you imagine them to be, but it knows it's in the debugger, so it went past there. It fetched the time. Actually, I can do this without the debugger. Let's try this. So we Alt F4 without optimization. Turn off optimization. Build again. Then the stepping makes more sense if you're not in the optimized code. When the code's optimized, some lines don't even exist anymore. So the source code doesn't match with the Hopper object code as well. So we do the same thing again. So now we're running unoptimized code in the debugger. Again, press F9 there, F5 to run there. F11, so again, what is F11? F11 is step into. So F11. So there we go. So now it's going to say, am I running in the debugger? If I'm not running in the debugger, there's no point setting the time because there's nothing to connect to. In other words, if I'm running just like this one, which is on a battery supply, it's obviously not running in the debugger because it's not connected to my Windows computer. But this one is connected to my Windows computer. So we're running the debugger, so it should get past that. Now it's going to get the time and date from my desktop computer. That's what this API does. Even though this code that we're looking at, this code here is running on the microcontroller, but it's making a call across the serial port to my computer to ask what the time and date is. And it gets it in this format, 24 hour. And if I briefly switch that back, push that out the way. I moved the video up across the serial console so that you could see the debug window here on the right. And you can see this is the time and date that it just got from my desktop computer. So 10:58 a.m. on the 14th of October, 2024. It's going to set the date and set the time. And this is in the real-time clock device. So it's getting them from the runtime, which is connecting to the serial port to get them from the computer. And it's setting them inside our real-time clock module here with these commands. And it's going to write a line to the serial console so that we can see that it actually did set the time from the debugger. So you should see this appear here in the right. So F10. There it is, set from the debugger. Success is true, successfully managed to set the time. And if it didn't successfully manage it, it would have returned false. But you have to consume the return values from results from function calls. And if you don't want to use it, you can throw it into this discarder. So this underscore is a placeholder for a variable that you're just going to throw the value away from. So the value returned was true and we threw it away. Because we don't really care if it was true or false, because if we're running outside the debugger, it'll be false. Then what do we do next? We go down here and we get the time, which should be slightly later now. Yes, it's 11 a.m., so it's like a little bit later since I've been talking since we got the time. And that's the format for time, hours, minutes, seconds. It's 24-hour clock, 24-hour time. And then if count is greater than 1, then we replace it with a space. If not, we're going to keep that colon. And now we're going to write the time string. So it's 8 characters long. Here we go, 8 characters. And our display over here is 8 characters long, yeah. So we should, after I F10 on this, there you go, 8 characters long. And it's 11 a.m. with some very ugly looking colons between. The colons don't really look like colons, which is why you can see, like, if I have 5 now, it's going to run continuously, and you can see my colons blinking now, and the seconds counting down. If I Control C in the debugger to stop it, we're now in the write text. So it broke into write text. You can see there's a call stack on the right here. Hopper, from there, display write, called write. And inside there, here we're looping through, and we're writing out for each module. So it takes that string and modifies it. It takes off the first four characters at a time, because there's 4 characters per module, and it'll display them to the module, whichever module it is, and it'll step through the modules. And that module there is a list of I2C addresses, and then it's writing the 4 characters out. And it also does some trickery, because there's actually a decimal point on these modules. You can see the decimal point. I'm not using it in this example, but I am using it in this example, and you can see it's blinking. So if there's a decimal in your string, it replaces it with a bit that puts it onto one of the other segments, so you don't use up a whole character for a decimal. It uses the decimal point as it's required. All right, so that's a pretty deep dive into this version of it. Let's switch back, and I'll break down and show you how the hardware works, so what hardware is supporting, before I move on to the next example. Subsequent examples should be a lot faster. So this was the Adafruit Feather one, with the Adafruit 14-segment display and the RTC SD at the feather wing. So let's unplug the power and see what we got. So this is the RTC. That's the real-time clock. Yeah. Let's move the other stuff out the way. This is the Adafruit board, and this is one of their new. Oops, I'm putting the whole thing out. This is one of their new RP. We can turn it upside down. You can read the name. This is the new RP2350 board, so the newer microcontroller from Raspberry Pi, and this was Adafruit's first available board with it. It has a LiPo charger built in, and you can have LiPo. Unlike the original from PiPico, it has from Raspberry Pi, it has a reset button, and it also has a USB-C socket. So these are nice boards. So that's the 2 components. This is the doubler, and in addition to putting headers on it, I also put some ones that have through pins, so that I can use it on a breadboard, and so that I can break out the power pin, break out the power, and break out the I2C bus. So that's that part of it. And then here, that's my I2C bus, and I've got it connected to 2 of these display modules. For one of the modules, I put header pins on it so that I can test the colors when I'm soldering. So I use this as a color tester, because the headers, when I'm soldering them onto other boards, because I have a lot more of these kinds of boards, the nice flush ones. Right, so that was sample number 1. And you can see, I mean, that's the doubler board with pins in it. And then in addition to the doubler board, they've got like a triple board too, which is what this one's on, the triple board. Okay, let's move this aside and move on to the next sample. This is my next sample. In this case, I don't have a coin battery in the real-time clock, but I have a LiPo battery connected to it. So it's never going to go powerless anyway, even though it's not plugged into a USB-C power cord. So same 14-segment display module from Adafruit again, and this is a tripler. And then this is a real-time clock, different real-time clock chip, but same real-time clock. And then this board here, this was the first available RP2350 board that has Wi-Fi on it. It's the Challenger board. I really like these boards as well. Again, they have USB-C and they have reset buttons, but decent Wi-Fi. The next one available is from Pimoroni, the Pimoroni Pico 2W, I think it's called. And I've got one of those in the mail, so I'll demo it when I get it. Yeah. Okay. So we can plug the power into this one. I mean, mains power. that little red light that went on, that's the charge light showing it's charging this, I believe. We're still going, it didn't stop. And now if I exit my program and go and look for, this is the Challenger one. So we've got Challenger Wi-Fi board. We've got the same display, and we've got a different version of the real-time clock. This real-time clock version, yeah, I think they both got seconds. Oh, this one in the alarm has seconds. So if you go and look at the real-time clock functionality, they have alarms, they can detect temperature. So depending on the real-time clock, I've got a number of different drivers implemented. So this one we're looking at right now is the DS3231. So it does have time and date. The resolution is seconds as opposed to minutes. Doesn't have any countdown timers. Some of the others do. Doesn't have any backed up RAM, RAM on board, SRAM on board that's backed up by the coin battery. But it does have a temperature sensor as well. So I could show the temperature on this one as well if I wanted to. The temperature that's being detected, over here by the real-time clock. Okay, let's go back and look at the program again. And should I build this without optimization in case we run the debugger again? So let's build this one. So pre-processing, compiling, generating. So the programs aren't completely identical because they're running on different hardware, and they've got different types of screens, different numbers of screens. But they're very, very similar. So I initialized the real-time clock. It's exactly the same line because all real-time clocks are called, RTC device. So even though the real-time clock itself is, from a different vendor, the actual unit name is the same. So that means that your code can stay more or less the same for multiple different devices. So initialize the real-time clock. The display is the same display, but I've only got one this time. So I'm only adding one unit, one module. Initialize the display. Same as last time, get the time from my computer and set it. And then again, I'm running in a loop. This time around for 4/10 of a loop. In other words, 40% of the time, I'll be displaying nothing for the colon. And for the other 60% of the time, I'm going to be displaying a dot for the colon. So when I do nothing, I replace the colon with nothing so that I end up going from an 8-byte. Let's do it in the debugger. That'll make it more obvious. So we load it up, uploading here, successfully uploaded. So let's go put a breakpoint on time string here. And you can see it stopped blinking as soon as I connected with the debugger. The period stopped blinking. And now it's blanked because I initialized it. Now we get that time string, and we look here, it's 5 characters long, and this is only a 4-character display. So what we're going to do is we're going to replace, you can see here there's a colon where my cursor is, and that should change to a period. So I replaced the colon with a period. And now the driver is going to combine that period into the digit before it, so it should be 1 period, so 1 period 09. So let's see what it displays. There we go. So 1 period 09. And when it comes around, when it goes over 4, the count's at 0 right now, then it should replace the colon with a space, and then it should just be 119. So let's see what it looks like when it flashes. I'm going to take away the breakpoint, F9, let's go. And there we see a flashing dot for the period. Anyway, you get the general gist. I'm going to speed this up so that I can take this apart and show you the bits again. So let's do that. Switch to the video. It says unplug the power. And this one's still on the battery, so I've got to unplug the battery. This is the microcontroller, Challenger board. One of my favorites. I love their RP2040 Challengers as well, and this is RP2350 Challenger. It's got a lot more flash on it than the PiPico, for example. So the PiPico 2, I think, has got 2 megs of flash, 4 megs of flash by default. So we use 1 of that for the program, for the firmware, for the Hopper firmware, and we use 3 for a flash disk drive, so it's got a disk drive on it. This one we use 1 meg for the firmware, and we use, I think, 15 megs for the flash drive on this thing. And the Wi-Fi is great as well. It's pretty reliable. And this is the LiPo battery. It's got one of these smaller plugs. One of the things I don't like about it is they reverse the polarity on their power plug. So by default, when you buy all these, they have, red and black. And by default, they're the wrong way around for this one. So I had to swap them around, and I put a note on there to remind myself it's reversed. This is the real-time clock. Very similar to the other one, except that it doesn't have the SD card thing. But the chip has more features on it. So like the countdown timer and the alarm being seconds precision. And then this is a different version of that display. So I'll show you the difference. Oh, I can't easily show you the difference, but it's more flush. It doesn't have circuit boards sticking out both sides like the other one did, and it's made to be feather form factor, so you can just plug it straight into feather, straight into one of these guys. Yeah. All right. So that's how the bits and pieces work in the Adafruit feather version. So the next one we're going to look at is one that's more like a Pi Pico. So let's move that aside. So this one's more like a Pi Pico. And I'll take it apart before the video and then put it back together again. Let's have a look at it. All right. So I've got my real-time clock in there from Waveshare. It's in the Pi Pico form factor with this little battery in. The little thing broke, so I stuck it in with a piece of tape. This is the Pimoroni board. I've put some colored header pins on so you can easily see like where the power pins are, what the pins are. Like I say, this is their Pico Plus 2. They've got a Pico Plus 2W coming soon. Unlike the Pico, it's got a boot button and a USB-C socket. Far preferable. And Waveshare marks which side is which, so you don't get them the wrong way around. So that's mounting it in the Waveshare real-time clock. And then this is another device from Waveshare, which is it's a 7-segment display, not a 14-segment display. But it also has periods, like little dots between each one. So we can plug that on as well, like that. All right, let's plug in the power. It should remember the time if my battery's still connected. It starts up. Yes, it does. 11:14 a.m. So let's switch back to our... put that a little bit bigger in there. How do we make that fit better? Maybe stack it up on this battery. It'll look okay. Yeah. All right. Different program again. Now I'm going to link to the source code. I'll put just up for the source code for each of these examples, and you can go compare them at your leisure. This is the Pimoroni version, because that's what the board is. And I just use the board for Pi Pico 2, because the Pimoroni is a drop-in replacement for the Pi Pico 2, so you can use the same board definition as the Pico 2. I'm using the WS there is my abbreviation for Waveshare. So it's the Waveshare 8-segment display and the Waveshare real-time clock. Same chip as we just used and showed in the previous real-time clock demo. So this is more or less identical, except that it's not this 7-segment display is not treated like a display because it's not I2C. It's got its own serial interface. So it's got its own clock pin, data pin. It's much older than the technology for doing these 7-segment displays is a little bit more ancient than actually it looks like it's SPI. Looking here. Yeah, it's just SPI interface, not an I2C interface. But it's a hand-coded driver specific for this device. So it doesn't say display begin, it says Pico 8-segment LED begin. And I tell it where the decimal position is going to be. And that's how I turn it on and off, because if you say decimal position 0, you don't get a decimal. And it's counting from the right, as in 1, 2, 3 from the right is where we want that dot to be flashing, as you can see in the video. Again, it gets the time from my device, and so it's slightly different as to how we're setting the time here. Because we're setting it as an integer, because this is a numeric display. So we're taking the time string and we're parsing out the first 2 digits and the last 2 digits as hours and minutes. And then we're recalculating that as a sort of a decimal. So hours and then 100, hours times 100 gets it into the left 2 digits, and then minutes. And then I'm counting to 100 here, and then for 40% of the time, I'm I'm showing the decimal, and for 60% of the time, I'm not showing the decimal. All right, let's build that. Compiling it again. And oh, let's not optimize again. So let me turn optimization off. So optimization off, build again. Easier to debug if you don't have the optimizer on. Much faster and smaller if you do have the optimizer on. But, you know, if you don't optimize, then there's a one-to-one relationship between hopper lines in the code and the hopper code that was generated for it. If you do optimize, you don't get the same, you know, it's much, the optimizer uses tricks. You end up with a lot less code. Okay. So I put a breakpoint where we get the time string. So let's do that. So again, and this display as well, it has to run through it really quickly. That's why there's no 100 millisecond delay here, because it doesn't stay lit. It has to keep refreshing it. It's a little bit like an old TV set where you have to continuously refresh the display if you want to see anything. Okay, so while it's stalled, you're only going to see one of the digits lit up like that. Okay, so if we get that time, there we go. It's 11, 18, and 13 seconds. Now here we're going to parse the hours part into hours. And if we look in the debugger, we see 11 for the hours, and now the minutes part into minutes, and that's 18, so 11, 18. Then time times hours plus minutes is going to be, there we go, 11, 18. So I multiplied the hours by 100. And then we're going to show the third decimal on this lap, so we're going to turn on the decimal point here. And now we show time, and we're actually passing it to an unsigned integer. Time is an unsigned integer here, so we're going to pass that into time. And it's not going to show the time, it's going to flicker it. Have a look at what happens on this display as soon as I press F10 now. See? Didn't really do what you thought it was going to do, because it has to run through and refresh them all the time. So if I run it in with F5 continuously, now you can see it's flickering. And it's kind of dim and pale, and you can kind of see that, you know, the dots flickering there. But that's because the debugger is running slower than if it was running in release, right? So let's try running it in release. So if we Control C, well, I could actually just, let's just load it up again. And then if I go like that, so it's slightly darker if I'm running without the debugger. So I pressed Control F5, which runs in the debugger, but without breakpoints. So it's faster. So it's less flickery. It's a little darker. And then the final version of demoing that is if we turn optimization on, so it'll run faster. What you'd think of as release mode on a Windows machine. Compile that. And it should still remember what the time is, even though when it's running in release, it's not running in the debug. So if I press Control F5 here, it's going to upload it and run it. Uploading. There we go. It still flickers in the video. So you can still see it fading in and out in the video, but in real life, when I'm looking at it, it looks pretty solid. I think it's just the frame rate in the video makes it sort of glow, flicker in and out. All right. That is so I've gone and shown you a whole bunch of toys today. Let's take them all apart and put them in a heap. Careful, there we go. And where are all the other ones? We showed you this other doubler, and we showed you those two. And also all of that mess. So there you go, that's the stuff we worked through today. Lots of different microcontrollers supported and peripherals supported by Hopper. And these were all boards that were running on the new RP2350 microcontroller. Part of the reason I'm doing this is I originally tested with the most simple real-time clock I could find, which is this guy. It's the 1307, and it has a simple little 8-pin chip, the real-time clock, and a simple little crystal. And I've ordered some through-hole components for these so that the next in my next demo of real-time clocks, I can add a real-time clock to the I2C bus on the 6502. So that's what'll come next. There'll be a 6502 version with a through-hole component real-time clock that we can add to the I2C bus on our 6502 computer. Anyhow, thank you for watching. And don't forget to subscribe and hit the like button. Cheers.